Okay, thank you very much for attending this talk. A little bit about me. I'm also the organizer of the Scala Madrid meetup group. This was created 10 years ago. Well, if you can buy to Madrid and want to say hi or even speak, you are more than welcome. I'm also a member of the program committee of Lambda World. Lambda World, I don't know if you know Lambda World Conference. Yeah. Well, this is the first year after the pandemic that Lambda World will be organized in October. The call for papers is open. You are welcome to submit some proposals. Well, it is a fantastic conference. It is very much like Lambda Days in spirit, in the sense that you will learn a lot and you will have fun. And the only difference is that it is not in such a beautiful city as Krakow, but it will be in a also very nice city like Cádiz in the south of Spain. So in this talk, I will talk about the implementation of an embedded DSL. What we will do is to discuss a preliminary implementation of embedding of the JQ language, the JSON query language, into Scala. Okay. And the main goal of this little exercise is to show why declarative programming, DSLs, domain-specific languages, embedded DSLs in particularly, are so important for software development. Okay. Moreover, we will discuss how to proceed. How do we implement all the different design concerns that we need to deal with in the implementation of a DSL, the syntax, the semantics, the dynamic typing, the type system, the deep syntax, the surface syntax, and so forth. And all this will be done following the guidelines of the tagless-final style, which is a way, a set of design patterns in order to implement embedded DSLs. Okay? And the last goal of this talk was also to illustrate some of the new features of Scala 3 that come in handy when we want to implement embedded DSLs. So for this talk, we will use a small sample. What we would like to do is to access the GitHub API in order to retrieve some information from the commits of a given repository. Okay? So in order to do that, we can leverage this endpoint from the GitHub API, and the result from this invocation and the result from this API will be a JSON document, in particular a JSON array that will contain all the commits from this repository that belong to a given page, because this endpoint is paginated. And the information that we want, let's say that it is the login of the author of the commit and living in the path author login, okay, and the date of the commit, which we can find in the commit author and date path. Okay, so the first thing that we had to do in order to solve this problem is first to create a string of pages. Okay, from the commit, from the repository, by invoking repeatedly the different this invocation, and to retrieve the different pages from the endpoint until we get the empty array, meaning that we do not have more commits. And then when we have this string of pages, what we had to do is to transform this string of arrays into a string of commits, flattening the different pages and keeping only the information that we want to put in an array. So how do we implement this? well, we are Scala programmers, we are functional programmers. There is a streaming library, which is called fs2. What we do in order to solve the first stage, okay, is to implement a function that will return a string of JSON documents that will be the different arrays. And in order to implement this lazily, okay, we use the pool abstraction of FS2. Okay, let me say that we will see a lot of Scala code in this presentation, but the important thing is not the Scala code. The important thing are the design patterns and the methodology that we will illustrate with this little example. My intention is that most of what I will say is applicable to the embedding of other DSLs and other host languages. You might be using Haskell, you might be using other languages, and the lessons to be learned from this talk, hopefully, will be also transferable to these other techniques. Okay, so do not, pay much attention, or do not get frustrated by the amount of Scala code that we will see. The important thing in this case, for instance, is that we repeatedly take a new page, okay, until the array of commits that we get is an empty vector. Okay. Now, concerning the second stage of our problem, what we want is, given a string of arrays of commits, what we want to do is to transform this string, okay, of arrays into a string of commits in which we get only the information that we need. This is essentially a string transformation function, and in FS2, this is called a pipe. Okay, so what we have to do is to implement a pipe, which can be done really easily by mapping each array of commits into a string in which we just keep the desired information, and then we flatten, we concatenate all these strings of commits to obtain the given results. And in order to extract the desired information from the commit, we use so that there is a lot of information. We just want the commit author date information, piece of information, and the author logging information. What we do is to use the optics that are integrated into FS2 and the CERC library, JSON CERC library, which allow us to access these fields using traversal optics, okay, in a rather convenient way. So again, it is not important to understand precisely the different lines of code, but keep in mind just that in order to implement this, we use the flat math from the FS2 library. We use traversals from Monocol. We had to convert a list of JSON arrays with the pair of information that we need into a string, and so forth, so forth. Okay, so can we do it better? Because this is a fairly high-level implementation. We are using higher-order functions from FS2. We are using optics and so forth. And the thing is that we can do it better. How? Because, for instance, with the JSON query language, what we can do in order to implement this pipe, in order to implement this string transformation, is just, you can do it with just one line of code, which is fairly declarative, because we can read this implementation in the following way. What we had to do first is to iterate over all the commits of each array in the input string, and then for each commit, we access the commit author date, path information, the author login information, and then collect all this information into an array, and that's it. Okay? So, comparing this solution to the FS2 solution, what we see is not only that we obtain a more concise implementation, also we obtain a fairly understandable implementation once you get used to the different symbolic operators that we have. Because, for instance, you see here these dot, square brackets, and so forth. And then, what is that? Well, okay, this is a small hurdle. Once you understand that this is simply the iterator, or that it allows you to expand a given array or a given object into a string, then it is fairly understandable. It is also this solution from JQ is really declarative in the sense in which you don't have to deal with lower level aspects in your implementation. In the FS2 implementation, you saw that we had to transform sequence into a string. This is not a point-free implementation in the sense in which we had to refer to variables and so forth. In the case of the JQ implementation, we just focus on the problem that we had to solve. And moreover, the JQ language has all what you need in order to implement this string transformation. In the case of the FS2 solution, you need to learn about FS2, you need to learn about optics, you need to learn about the size JSON library, and so forth. In the case of GQ, it is all integrated into the same language. Okay? So this is really nice. On the other hand, in the FS2 solution, what we saw is that we were also able to implement the all pages functionality, the functionality that allows us to create this string of pages, okay, and to iterate over the endpoint until we got an empty array. We could do that because in the FS2 library, we live in the Scala ecosystem, and we have plenty of libraries that we can exploit in order to solve our problems. Okay? Whereas, in the case of JQ, our solution is, I mean, it's out of the scope of this wider context. Okay? So, what we would like to do, of course, is to obtain the best of both worlds. And the way to do that, of course, is to embed the JQ language in a Scala in such a way that we would be able to write our pipe in FS2 in this way, in a way which resembles almost exactly the syntax of the JQ program. Okay? Well, this is the purpose of our talk, is to show how can we write this program, how to embed the JQ program in Scala in such a way that we can use it in a complementary way to with FS2. Okay? So how to do that? What we will do is to leverage the tagless-final style, which is a style of for embedding DSLs into general purpose programming languages that was put forward by Oleg Kiselyov and colleagues in this paper. What I really like about tagless-final is that it favors a step-by-step methodology whereby you will implement the different concerns of your DSL in an incremental fashion. Okay? And in this presentation, what I will do is to divide the implementation of the DSL into these major 4 steps. In the first one, what we will do is to create a version of our DSLs that will only work for FS2, for the FS2 streaming library. Okay? Then what we will do is to, okay, I would like not only this DSL to be usable by FS2 developers, but for instance, AK-string developers. Okay? And then we'll create a new version of our DSL in which we will essentially perform a process of domain abstraction. Okay, let's abstract the particular features that are related to FS2, and let's see what happens. Then we will deal with dynamic typing, and finally with static typing and type systems and so forth. So let's start. What we recommend is to start implementing a DSL considering specific problems, specific programs that we want to write. We would like to write this program. Okay, so in order to write this program, we need a little piece of syntax. What do we need? We need the iterator operator, we need array combinator, we need this indexing operator, and the pipe, of course. Okay, we need to an operator that allows us to feed the output of some filter into the output of another filter. Okay, and well, we just write functions for each of the operators and combinators that we need. Okay, where is the syntax? The syntax are these functions. In the tagless-final style, we do not define an algebraic data type or a data type in order to define our program types. No. What we do is just to use functions. It is a purely functional approach to the implementation of DSLs. Now, and what we see here is that, well, this is Scala 3, and you may have noticed that there are no curly brackets anywhere, which is really nice. I will emphasize some of the features of Scala 3 that are also used. For instance, in this case, what we use are extension methods in order to implement in fixed operators. Okay? Now, in this first implementation of our language, what we will do is to implement our DSL for a particular semantics. And this semantics means that our filters are string transformers. Filter is the name in the JQ language that to refer to this feature. Filters in this implementation are just pipes, FS2 pipes. And the implementation of these operators will be, will be tailored for the FS2 semantics. So the iterator constructor will be implemented in terms of flat map. Okay? We receive a string of arrays, of JSON arrays, okay? And then what we will do is to map these arrays into a string. We will flatten the string, and then we'll concatenate that. I mean, essentially a flat map. What if in the input string we do not get an array? Well, this will be an error. We will deal with this kind of errors later on. Okay? For the moment, we just keep this simple. Now, what we have to do in this first stage, in this first step, is also to consider that, for instance, in the JQ specification, the .author.login expression is not primitive. Okay? This .author.login expression in JQ is actually syntactic sugar for a number of other operators. For instance, .author.login, it is essentially accessing the author field of some object and then feed this output into this other filter that will retrieve the login field. Okay? And the .author, it is still syntactic sugar for the identity filter that will be indexed through a string author. But this string author is again a filter in JQ. It is a constant string filter. Okay? Similarly, with this notation for creating an array of these two fields, what we have here is not a built-in syntax of comma-separated arrays. This comma here, it is the concatenation operator in JQ. Okay? In such a way, what we are doing here is to concatenate the output of these two filters, and then the array constructor receives just one only filter. Following this, what we had to do is to refine our initial syntax in such a way that we are able to distinguish between the deep syntax, okay, and syntactic zero, the surface syntax, all right? And the surface syntax, the operators from the surface syntax, for instance, the array that takes a lot of filters, okay, this will be implemented by building upon, okay, the array primitive filter and the concat operator, okay? And similarly, in this first stage, we will also take into account that, for instance, in the JQ specification, there is a built-in library of keywords and operators. For instance, the map combinator receives a filter, and then it applies given it expands a different array, then applies this transformation, and then collect again all the information in an array. This has to be implemented in our case also as a derived operator, as a derived combinator that makes use of the primitive combinators and constructors that we deal with. So, in conclusion, what we have in this first version of our embedding, it is an ad hoc version of our language for specific semantics, which is structured into these three categories. Okay, now we have one implementation that is strongly coupled to FS2, but what if I am not a user of FS2? I'm a user of, let's say, CO streams, or we are users of ACA string. What we will have to do in that case is to copy-paste our implementation, okay, and replace all the implementation of the primitive filters. But in red are implementations that wouldn't change at all. Okay, so this is a problem, of course. This copy-paste is a problem, and what we will do in the next step is to solve this little problem. How? Well, what we will do is to perform a process of domain abstraction, using which technique? Type classes. Okay? Type classes will allow us to abstract away the particular semantic domain in which we are using, we are implementing our language. And the primitive filters, the primitive operators and keywords combinators and so forth will be left abstract. But of course, the built-in functions will be able to be reused with any instance, with any implementation of this type class. And similarly, the surface syntax will be also able, that it is commonly implemented in a separate module, will be able to be reused across all the different legal instantiations of this type class. Okay? Now, how do we implement our FS2 transformation, our FS2 pipe? Because this is our problem. Well, what we had to do is just to instantiate our JQ type class with our desired semantic domain, with our desired representation, which in this case is the pipe. And then the implementation of the different primitive combinators will be exactly the same as before. And the same for the program that we wanted to implement. The same program exactly. Okay? Yes? No? Yes? Now, what we can do once we have this type class is to program at a general level of abstraction. I mean, given that we have this type class, which essentially specifies the syntax of our domain-specific language, what we can do is to program against the type class and implement our program for any kind of semantic domain, for any kind of representation. This program, written in this way, this is an ad hoc polymorphic program, can be reused with FS2 pipes. It can be reused with ACA strings and so forth. Okay? And we, in Scala 3, what we can do is also to implement this polymorphic program using so-called polymorphic function types and polymorphic and context function types. But importantly, this is not necessary. Okay? We do not need to write at this level of abstraction because we could be comfortable writing in FS2, right? Okay. Now, let's move on and let's deal now with the issue of dynamic typing. JQ is a dynamically typed language, which means that type errors may occur, but they will occur at runtime. Okay? For instance, this program is simply iterate over the arrays that will be received in the input string. Okay? Well, this will work without problems, of course, if in the input string all that we receive are arrays, right? But what if we receive a Boolean? Well, there will be an error, okay? And this error will be at runtime. In JQ, we can also throw custom errors, and we can catch errors, okay? So, how do we incorporate all this in our embedding? What we had to do first is to declare, to define, and we will do it with this new feature for implementing algebraic data types, okay? And here we declare all the different type errors that we can have so that they can be reused across the different semantics that we want to do. And then for a particular semantics, what we had to do first is to acknowledge that in a given string transformation, in a pipe, the result could be not only a JSON document, but also an error, okay? And this will be taken into account, of course, in the implementation of the different primitives. For instance, in the iterator that we left unimplemented partially before, we can complete the implementation now, acknowledging that if it is not an array, what we receive in the input string, then we will return an error, right? Okay, this is nice, but let's compare now these two programs. In the first one, this is the one that we analyzed before, there could be errors at runtime. Okay, why? Because okay, I do not know the components of the input string. If all the components in the input string are arrays, perfect. But if they are not, there will be an error. I mean, we cannot do anything about that. But what does it happen in this program? In this program, what we are doing is using this constant string filter. Hi, it is a string transformation that essentially what we will do is to output hi. Hi, 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 hi. Okay? All the time, strings. And this is feed into this other filter, but this other filter is the iterator filter. It requires an array. Well, we know beforehand, we know well before we run this program that it will fail, always. It will always fail. So what we should do is to reject this program at compile time, okay? And this is the issue of our next version, how to implement static typing in our language. Even if our domain-specific language that we are trying to embed is a dynamically typed language, okay? But, well, we are embedding this language in Scala, which is a strongly typed, which has a strongly typed system. And so our intention in this new version is to exploit, to get advantage of this static type system from Scala in order to implement a a statically typed version of JQ. That allow us to get rid of these malformed programs. How to do that? Okay, let's analyze this program. Why it is wrong? Well, it is wrong because what we have here is a filter, a string transformation, that will always output strings. And it will receive types of element, whatever, okay? What we have here is a filter that requires, demands that the input JSON that will be encountered in the input string, they had to be arrays, okay? And this program says that the pipe is a combinator that takes the output of the first filter and feeds this output to the input of the next filter, provided that they match. If they do not match, I mean, it doesn't make sense. It should be rejected. Now, let's formalize this intuitive explanation. We can do that using a type system. A type system is nothing else but a set of rules that will allow us to assign types to the expressions of our language. So, in this case, what we say is that we have a string, this expression, is a filter that receives values, JSON documents of any type, and they will return strings. What we have here is that the iterator combinator is a filter, it's a string transformer that will receive a string of JSON arrays, and then of type A, and they will return a string of A's, okay? And in the case of the pipe combinator, what we have is it is a combinator that attempts to combine filter F1 and F2. The first one will output a string of elements of type B. The second one receives a string of elements of type B, and then what we return is a string transformer of JSON elements of type A into type C, okay? And of course, the key here is that these two types have to match. Now, to match doesn't mean to be equal, okay? Because, for instance, in this case, what we have is, in this case, what we have is a filter that outputs strings, okay? Let's say F2 is a filter that receives JSON, whatever JSON documents, and of course this is legal. And this is legal because JString conforms to JSON, okay? We can pass strings to a filter, to a strings transformer that receives any kind of JSON, okay? So this is legal. How do we implement this type system into Scala? Well, the first thing that we need to do is to implement our types, the filter type, okay? And in order to implement the filter type, what we will do is to exploit contravariance and covariance from the type system of Scala. We want the first type argument of the filter type to be contravariant and the second one to be covariant. We will use this hierarchy of JSON elements, okay? We have nulls, booleans, numbers, strings, arrays, and objects, and so forth, okay? Notice that we declare this filter type to be sealed, which means that we won't be able to instantiate this filter. Why do we want that? Well, we do want that, and it doesn't matter that we won't be able to instantiate this type, because this type will only be used at the type level. It will only be used to implement the type system of our language, okay? Let's see how to do that. What we will do is to annotate, essentially to annotate the different, to tag the results from the different and the inputs from the different combinators in such a way that we can track all the types of filters that are being generated. This is the implementation that the untyped implementation that we were working with in the last versions. What we have is that The JQ type class is parameterized with a representation, an arbitrary representation R, that, for instance, the string filter, the string constructor will return a pipe, an ACA string, or whatever, okay? And let's see what will happen now. What will happen now is that first, well, this is the implementation. There are lots of characters here. It got polluted somehow. It's more complicated, yeah? But if we understand what is going on, it is not that complicated. First, what we have to notice is that the type parameter in our type class is no longer a simple type. It is a type constructor parameter. How we will use the parameter of this type constructor? We will use that parameter in order to annotate, to tag the type of the filter that we are constructing. So for instance, here, the result is not just, okay, the result is not just an R, but a filter that receives any kind of JSON and returns a string, okay? And here, what we have is an iterator that receives strings of arrays of type A, and then it will return a string of A's. And for the pipe, okay, what we have is that the input are filters of that receives A's and returns B's, and B and C, and so forth. Okay, this has a one-to-one correspondence with the type system rules that we saw before. So when we understand the whole picture, when we understand that what we are doing is implementing this type system, it is no longer such a problem, okay? Now, and with this annotation, type annotations, okay, what we are able now is to get rid of this program. What we will obtain is a compilation error. And the compilation error from Scala, this is not exactly the error message that is generated by Scala. The error message by Scala is that. Okay. Here I had to simplify it a little bit, but it is fairly understandable. Hey, I found a filter that receives arrays and returns whatever, and what is required is a filter that receives strings, a string of strings. Because here what you have is the constant string filter, okay? Now, concerning the semantics, which are the changes? Because we have to instantiate our type class, okay, with fs2. Well, it is no problem. The only difference is that the semantics is the same exactly. Okay, 7 minutes. The semantics is exactly the same. The only thing that will change is that, of course, my type class is parameterized with a type constructor. But I don't care about the parameter of this type constructor. It doesn't care. I do not care. Why? Because my object language is not typed. Okay? A pipe, there are no types here. This is JSON, okay? So no problem. And what we have in effect here is some kind of type erasure. Okay? The type system is only in effect for at the type level, at compile time. At runtime, we do not have these filters at all, these types at all, right? Now I have another example for the type system which allow us to illustrate in a very nice way union types of Scala 3 and match types, but I will skip this part, okay, and then jump to the conclusion. Okay, so why is declarative programming so important? Why should we care about DSLs? Well, in the Helm talk, this before lunch, the speaker said something that I really like it. I mean, Helm was designed with the purpose of making programmers happy, with programmer happiness in mind. Well, this is the purpose of all DSLs. The purpose is to allow the programmers to think declaratively, to think, to reduce conceptual noise, to remove accidental complexity, to focus on your problem. Okay? In the case of JQ, you have strings of JSON, you want to transform JSON streams, and then you have all what you need in order to focus on that. You do not need to learn about optics, you do not need to learn about the strings and transformations from lists to strings and so forth. Okay, you have all what you need and you can focus on your string transformation. This is really nice. And embedded DSLs, what allows you is to reuse and to exploit all these high-level abstraction languages within your ecosystem of general purpose ecosystem, which is really, really, really nice. Well, what about how to proceed? What we did is to illustrate all this approach of designing our embedded languages using the tagless-final style. And what I really like about tagless-final is that it allows you to proceed step by step in an incremental fashion. I mean, maybe you were scared about the type system version. Okay? Maybe you were scared about these rules and type constructor parameters and so forth. Maybe it is not needed for your language at all. Okay? Don't worry. Maybe you do not know much about type classes and this technique of domain abstraction and so forth. Well, maybe you do not need it. Maybe you work with FS2 and it is okay. Okay? So it is important also to keep things simple. But notice that the ultimate goal of functional programming is to implement to develop software applications using a functional architecture. And a functional architecture is an architecture built on DSLs. And in order to do that, we had to really come up with reusable implementations of our languages. And it would be a pity to have an embedding of JQ in Scala that could be used only with FS2. Okay? And that we had to copy and paste all this implementation in order for using it with AK string. Now, concerning Scala 3, we saw that there are many features of Scala 3 that we can profit from to implement this. Embedding, extension methods, the new features from type classes, polymorphic function types, and so forth and so forth. Really nice. But I would like it to have been able to show you also this an illustration of these new features from Scala 3, which is the combination of macros and structural types, which would allow us to implement the indexing filters in this way, not with strings, okay, but with keywords, okay? And in such a way that if we want to index, for instance, this JSON object with fields A and B, and we try to access the C, then a compilation error will be thrown, okay? And this can be done with macros and structural types. Now, this exercise of implementing JQ in Scala was intended as an aid to our training on DSLs in our computing, but we decided to make public all this stuff so that you can contribute for the development of the language. Because, well, it might be a good idea to use JQ with FS2 and so forth, and you will learn a lot. In order to do that, if you want to dive into this process, I recommend you to, this was not on purpose, okay? I recommend you to check out the documentation from Oleg Kiselyov. We have also some information in Abla Computing. We develop trainings and consulting, but you have these public GitHub repositories with information useful for doing tagless-final. And then just to finish, I want you to leave these references in case that you don't like tagless-final. There is some alternatives. You don't like JQ, well, you can do also quite nice with optics and so forth. So thank you very much.